morning everybody. Today I will start with electrochemistry. It is a branch of chemistry that studies the relation between electricity and identifiable chemical changes, where electricity can be cause or electricity can be output or effect. Now, reactions involve electric charge moving between electrodes or an electrolyte. Okay. So, it deals with electrical energy and chemical changes. Now, production of electricity from spontaneous chemical reaction, a large number of like metals, chemicals like sodium hydroxide, then chlorine etcetera are produced by electrochemical techniques, batteries, fuel cells etcetera. Here also electrochemistry is an integral part. Now, reactions that are done with this electrochemical technique, these are basically in some cases these are eco friendly and they do not generally produce pollutions. Now, also the signal transmission in living system is also known to have this electrochemical in origin. Now, when we talk about electrochemistry, then the first thing that comes is conduction. So, conduction means conduction of electrical charge across some circuit. Now, basically here whenever we talk about conduction, then different type of conductors are to be considered. One is this metallic conductor, another is non-conductor or insulators, another is semiconductor, and the fourth one is this electrolytic conductors. Now, electrolytic conductors means whenever we measure resistance across those materials like electrolytic conductors, then this resistance is arising as a result of something which is a little bit different from what is observed in case of say metallic conductors. Now, in metallic conductors what is happening, that suppose this is a conductor. So, you are applying some potential difference across this circuit. So, electrons are transported from this side to that side. This is transported from this side to this side. So, as such from outside there is no change in the material, that is in the conductor. Now, when it is the case of electrolytic conductor, the situation is a little bit different, that you have a solution, okay, and you are immersing two electrodes. So, one is plus, another is minus, and when you measure resistance, that means some current is flowing across these two electrodes. Then what is happening, that in this case this ions which are there inside this solution, these are responsible for the carriage of charge from one place to another. Now, so different types of conductors, like good conductor. So, these are almost fully conducting, almost fully conducting. Semiconductor, this is partially conducting. Insulator, these are not conducting. Okay. Now, I have just talked about this conduction through metal and conduction through electrolytic solution. Now, what are the typical differences in this metallic and electrolytic conductors? So, in case of metallic conductor, the electrons are transported from one position to the other, and in case of say electrolytic conductor, ions are responsible. Ions means, when we talk about ions, that means the substances which when are dissolved in some solvent, then they will produce ions, and those ions against some applied potential difference, they will move in a particular direction depending on the direction of the applied electric field. Okay. So, in this case, in case of metallic conductor, so no transport of matter, no transport of matter is there, but in this case electrolyte or ions are transported. These are transported. Now, third difference can be like the resistance is almost proportional to temperature, and in this case generally resistance decreases with rise of temperature. This is just a rough approximation. I am not telling that exactly it is followed, but this is a rough approximation, and in this case no chemical change. But in this case chemical change is there at the electrodes, chemical change at the electrodes. Okay. So, these are the few these are the differences between a metallic conductor and electrolytic conductor. Okay. So, now let us move on to another thing which is common, that that whenever we talk about this conductivity, then or conductivity or resistance, that means when you talk about this conduction of electricity, then one thing which is very important, one parameter which is very important is the resistance of the medium. Resistance. Now, resistance it is basically proportional to length of the conductor, and it is inversely proportional to the area, cross sectional area of the conductor. So, for compound variation we can say R is proportional to L by A, or we can write is equal to rho L by A. It is rho is basically the specific resistance or resistivity of the medium. Okay, so it is the resistance of 1 meter long conductor, and if the cross sectional area is a unit, then it will be called as the corresponding resistivity. Now, in terms of conductance of a solution, the generally used term is the conductance. It is not expressed in terms of resistance, but it is expressed in terms of conductance. So, conductance is nothing but inverse of resistance. So, conductance is inverse of resistance. Okay. So, what you can write, so conductance is equal to 1 by rho into A by L. I mean, from here we can write like this. So, this was specific resistance or resistivity, and this is specific conductance or conductivity. So, unit of resistance is ohm and unit of conductance is ohm inverse or MHO, and in SI system it is Siemens. Okay. So, therefore, we can write conductance is equal to specific or conductivity into A by L, or we can write from here, we can write specific conductance is equal to conductance into L by A, which is basically a term which is given a new name, cell constant. Why do we write cell constant? I am coming to that. So, specific conductance. So, let us talk about unit of specific conductance. Specific conductance equal to conductance into cell constant. Conductance is Siemens into cell constant is L by A. L by A means length inverse. Okay. So, that means Siemens, if it is centimeter then centimeter inverse, or if it is meter then it is meter inverse. Okay. So, it is, if it is meter then Siemens meter inverse if it is expressed in meter, but it is SI system. So, therefore, it is better to use meter rather than centimeter. Okay. So, specific conductance is given a symbol kappa. So, kappa is equal to conductance into cell constant. Now, let us come to the point why it is a cell constant. Now, whenever we measure an unknown resistance, okay, whenever we measure an unknown resistance, we generally use this celebrated Wheatstone bridge principle. Now, this Wheatstone bridge principle is basically having this diagrammatic representation. Say this is your unknown resistance R1, R2. You have a device that which is in most of the cases is a galvanometer. Source of electricity. So, when the deflection is, when it is there is no deflection, means the bridge is balanced. Then ratio of these two, this by this equal to this by this. So, R1 by R2 is equal to R3 by R4. So, from this R1 you can write R3 by R4 into R2. So, if this, and this is a variable resistance. So, you can have this balance of this galvanometer deflection, that is balance of this bridge when at some appropriate value of R2, then you can at the balanced point Okay. So, this way you can find out the unknown resistance R1. Okay. So, now when it is solution means you have an electrolytic conductor other than, it is not common this metallic conductor or some other kind of conductor, then you have these two electrodes and you have to measure the resistance across these two electrodes. Okay. So, across these two electrodes means you need to have one electrode over here, another electrode over here, and then this 2 watts are basically these 2 watts. You have to connect this one. This is represented like this. Your electrolytic cell is represented like this. Okay. So, this is one unknown resistance, say R1. So, you place this over here. Okay. So, your this diagram looks like this one. So, you have to replace this with this one. Okay. Now, there is a little bit difficulty in measuring this resistance or conductance of this electrolytic conductor. This is because of the fact that, as I mentioned to you earlier while discussing the difference between a metallic conductor and an electrolytic conductor, that is there is some chemical change at the electrodes. Okay. So, since there is a chemical change at the electrode, then during measurement of the resistance of this particular cell, then the characteristic of this material is getting affected. Okay. So, therefore, that is why you have to construct a cell like this, that you have your unknown solution kept over here, electrolytic solution kept over here, you dip 2 electrodes and then you measure resistance. But while measuring resistance, you have to be very careful that in this case, in most of the cases when you use this Wheatstone bridge, then you supply a DC current. Okay. In that case, there is no problem in the measurement of the unknown resistance, but the moment you use DC current for this, then there will be electrolysis or various electrode processes. So, electrode is getting affected, and if the electrode is getting affected, then you are not going to get the right value of R1. So, in this case what you have to do? You have to make use of a different technique, but the same Wheatstone bridge principle, but here in place of a DC supply you have to use AC. So, AC means it is a cosine profile as a function of time, in this case intensity of the field, and this is your time. So, what is happening that in the say first positive half cycle, if this electrode is positive, then the other electrode is negative. In the next half cycle over here, the polarity is reversed, this becomes minus, this becomes plus. And if this alternation is symmetric, that is area under the curve over here and area under the curve over here, these two match, then what is happening? Then in the positive half cycle, whatever is generated over here and also over here, the reverse is generated. But the point is, so therefore, what is happening? If a simple electrode is used, then the accumulation of various material is there, especially when you use water as a solvent, then electrolysis product of water, that is oxygen and hydrogen, these are produced in equivalent amount on each of the electrodes. So, electrode will be affected in the sense that it will be covered with those gases. So, therefore, characteristic of the electrode will be changed. So, therefore, in this case if you use a platinized platinum electrode, platinized platinum electrode means it is a smooth platinum plate on which this finely divided platinum metal particles are deposited on this, and these are acting, this can act as a catalyst for the recombination of oxygen and hydrogen to produce water. So, therefore, electrodes will be freed from these accumulating gases. So, therefore, electrode characteristics will not be changed, and as a result of which you can measure the actual resistance across these two electrodes. So, basically you are putting this cell over here, that is why the cell constant is coming over here. So, cell constant is nothing but it is the ratio of the length between these two electrodes. This is your L, and A means this is your A, this is the area you are talking about. Okay. So, therefore, L by A is the cell constant. Okay. So, this way you make use of this AC supply to measure the resistance, I mean the conductance of the cell, that means conductance of the cell which is containing your required material. Now, how will you identify this balance point of this Wheatstone bridge? This is done in a little different way. So, here this frequency of AC is about say 500 to say 1000 hertz or similar values are there, and when the bridge is balanced, that means you change your R2 in, or you adjust your R2 in such a way that if you put a headphone over here, then minimum sound will be there, and therefore you will get a confirmation that this bridge is balanced, and at the balance point whatever values of these are there, I mean R3, R4 and R2 is there, make use of this to find out the value of your unknown resistance. That means, in turn you measure the conductance of your unknown solution. Okay. So, therefore, what is the expression that you generally use is specific conductance is equal to conductance into cell constant. Okay. Now, let us have some idea about various conductors, various materials as far as their conductance values are concerned. So, if you consider materials like materials and their conductance, it is in Siemens meter inverse. Okay. So, say for example, copper metal, its value is about 6 into 10 to the power 3. Silver, its value is about say very close to this value, I mean copper value. Okay. Glass, its conductivity is very low, it is about 1 into 10 to the power minus 16. Pure water, it is about 4 into 10 to the power minus 5. For example, if it is 0.1 molar HCl, its value is close to 4. Germanium, it is about 2. So, you see that if you think about these two and think about this metallic conductor, then its value, I mean this conductivity is very high. In case of pure water, it is very low, but it is much better than glass or some other non-conducting material. In case of this 0.1 molar HCl, it is about 10 to the power 5 times more than that of pure water. Okay. So why this is happening? I mean the clear cut answer is that in 0.1 molar HCl you have H plus and Cl minus ion. So these are responsible for the transport of electrical charge from one position to the other. In case of pure water, it is feebly ionized. Water is feebly ionized to H plus and OH minus, very feebly ionized. So therefore, since the ions present in water, in pure water, so these are very less in number, therefore conductivity is quite low. Okay. So this gives you some idea about the conductivity of various materials. Next we will move on to another quantity which is called the molar conductivity. Molar conductance. Molar conductance is the conductance of a solution which is having 1 molar substance dissolved in water, and it is measured with 2 electrodes. Those are separated by these 2 electrodes are separated by unit distance 1 meter. Okay. And whatever conductance value you are getting, it is called the molar conductance. Okay. So molar conductance is basically given in notation lambda m, and lambda m it is expressed as kappa by concentration, where lambda m is having unit Siemens meter square mole inverse, where kappa is expressed in Siemens meter inverse, concentration is mole per meter cubed. Okay. Now, if we would like to know how this molar conductance will depend on concentration of the material, but before that let us have some idea of how simple conductance will vary with concentration and other factors. Okay. So before that let us have some idea. So conductance, as I mentioned, that it is due to the transport of ions across the electrodes. So therefore ions means things are to be considered are basically number of ions. So that means if more number of ions are there in the material, then it is expected that the amount of charge that will be transported across the electrodes will be more. So number of ions is very important. It is an important factor. Then charge of the ion. Okay, charge means suppose you have say M plus, say M1 plus, say M2 2 plus, and say M3 3 plus. Okay. Suppose you have M1 ion with unipositive charge, say M2 ion, M1 ion, M2 ion and M3 ion with bipositive charge and M3 ion with tripositive charge. That means, one ion contains 3 unit charges, this ion contains 2 unit charges and this ion contains only single charge. Then suppose if this ion is transported across this 2 electrodes from here to here, say M1 plus, then only 1 unit of charge will be transported from here to here. If M2 plus is transported, 2 plus is transported from here to here, then if the other factors are remaining same, then you will be saying, you can tell that in the same time or in the same duration, suppose these two are reaching this side in same time, like T1 time and here also T1 time, then the amount of charge that is carry forwarded from here to here, it will be double for this, it will be triple for this. So, therefore, charge of the ion is very important in the conduction process. So, therefore, conductance will also depend on the charge of the ions. And next one is the speed of ions. Speed of ions. Suppose you have 2 ions, say ion 1 and another is ion 2. Say this is also unipositive, this is also unipositive, but the thing is that suppose that it can swim faster than this one, that is its mobility is more than this one, then in same time interval the amount of charge effectively it will transport more charges than this one, because it can move faster than this one. So, therefore, that is why these are the 3 important parameters, important factors that are needed to be considered while while discussing the conductance of a solution. Okay. So, therefore, when a solution is diluted, what do you expect to have? Suppose you have 1 molar, suppose you have, say for example, 1 molar say NaCl solution. Suppose you dilute to say 10 to the power minus 2 molar and then you measure its conductance. Okay. Some value you can expect with the help of your device, that is this using Wheatstone bridge principle. So, some value you can expect, that is maybe say for example, x is the measured conductance. Now you dilute it to say half into 10 to the power minus 2 molar. Okay. Initially it was this much, now it is half into 10 to the minus 2 molar. Then conductance is expected to be reduced. Why? This is because of the fact that the number of ions, that is present in a given volume, it is now reduced. Okay. Number of ions is reduced, and since number of ions is reduced, therefore conductance is expected to be reduced. So, go back to the formula, specific conductance equal to conductance into cell constant. So, cell constant is remaining same. So, what you are doing? You are diluting the solution. So, what happens to specific conductance? What is specific conductance? It is the conductance of a solution which is placed between 2 electrodes unit distance apart, say 1 meter apart, and also the electrodes are having 1 meter square cross sectional area, 1 meter square cross sectional area. So, if you dilute it initially, say for example, x number of say ions, say for example, say x prime number of ions were present in this unit cube. Now, if you half dilute it, then this becomes x primed by 2. Okay. So, x primed by 2 means your number of charge carrier is reduced to half. So, number of ions is reduced, then charge carried by ions, charge on ions, no change, and speed of ions. This is also you know, you can consider this, that this one is also remaining unchanged. So, therefore, since the number of ions is reduced, specific conductance decreases, cell constant is fixed. So, therefore, conductance is expected to be reduced. Okay. So, therefore, again come back to molar conductance. So, that we started to talk about, and in between we wanted to, you know, learn about how conductance is dependent on various factors, and we have, you know, explained to you that there are the major, I mean, 3 factors. One is number of ions, another is charge on the ions, and speed of the ions. So, molar conductance is lambda m, which is nothing but your specific conductance kappa by C, where C is mole per meter cube and kappa is Siemens meter inverse. Now, if you now plot molar conductance, that is lambda m, with square root of concentration, it has been found that for the strong electrolyte, the curve follows like this. That is, if you dilute it in this direction, if you dilute it, then molar conductivity increases. So, why is this so? Why molar conductivity should increase when you dilute the solution? Now again, lambda m is your kappa, it is your conductance, okay, then specific conductance, and then inverse of cell constant. Okay, that means A by L. Okay. So, the idea is that you have to place your solution, against or in between 2 electrodes that are separated by unit length. L is equal to 1. Okay. So, therefore, if your volume of the solution is V, then effectively area of the electrode is nothing but V is equal to A into 1, because A is the area, because you have to place your entire solution in between 2 electrodes, those are separated by unit length, and there is no restriction of the area of the electrodes. So, therefore, area is freely changeable depending on the dilution of the solution. Therefore, you can write from here V is equal to A. So, therefore, from here you can write lambda m is equal to kappa into volume. Okay. So, therefore, how does lambda m change as a function of dilution? So, when you dilute means volume is increasing, okay. And what is going to happen to kappa? Very simple, that as I already explained to you here, that when you dilute, then kappa is reducing. So, therefore, there are 2 opposing factors. One is kappa, which is reducing as a result of dilution, and volume, which is increasing as a result of dilution. So, what is going to happen? That ultimately it has been found that the effect of change of volume is much more than the effect of dilution of, effect of lowering of kappa. So, therefore, in effect lambda m is found to increase. So, therefore, that is why lambda m as a function of square root, if you plot it follows a trend like this, but only thing is that important point to note is that this type of linear dependence, is observed for strong electrolyte. Strong electrolyte means the electrolyte which is completely ionized when you dissolve it in water. Okay. But the situation is not so easy, I mean it is not like that, like a linear dependence for a weak electrolyte. Okay. So, for weak electrolyte what is happening, let me draw it again in another piece of paper. For weak electrolyte, the plot, it is square root of c and this is lambda m, it follows a trend like this, whereas the strong electrolyte follows like this. So, this is CH3 COOH and this is, say for example, KCl. So, this is quite understandable, I mean why this is increasing like this, but in case of weak electrolyte you see that as you dilute it, there is not much perceptible change in the higher concentration range. Say for example, if your concentration is in mole per liter and the value Siemens centimeter square mole inverse, then say for example, it is say about 200 and here it is say for example 0.2, 0.4, these values are 0.4 okay, and 0.2, then you see that in higher concentration region it is almost flat. Okay. It is following the same trend as your this axis, it is parallel to almost parallel to x axis, but when you decrease the concentration it follows a trend like this, and in very low concentration region it steeply rises. So, why is it happening? This is something strange. Why strange? Because it is unlike this strong electrolyte, this is following a different trend. Why it is like this? Now, one thing that you should take into account, that this CH3 COOH, it is a weak electrolyte. So, it is not completely ionized. So, if you dilute it, then its ionization increases. So, that means CH3COOH, it is mostly in this form CH3COO minus. So, degree of dissociation, if it is alpha, then 1 minus alpha, then alpha, then alpha. So, therefore, degree of dissociation, since degree of dissociation is very small in moderate concentration range, therefore, number of charge carrier that is less in this region. The moment you keep on, the moment you increase the dilution, that means if you add more of water, then the degree of dissociation, the amount of dissociation increases, and therefore what happens, that whatever factors were there, like lambda m is equal to kappa into V. So, V factor is there, V increases, at the same time this kappa is also increasing, because if you dilute it, then number of ions, number of charge carrier increases. So, total number of if charge carrier increases means your kappa, although there is a dilution effect, but the effect of this increase of charge carrier is coming into action, and as a result of which a nonlinear dependence of nonlinear dependence of this this lambda m versus root over C plot is there. So, in case of strong electrolyte, this for strong electrolyte lambda m, that is the molar conductance, follows a trend like this lambda m 0 plus a square root of C, where lambda m 0 is a constant quantity, and you can understand from here that if you go close to 0 concentration, that is infinitely dilute condition, then whatever lambda m value you are expecting, that is nothing but lambda m 0. So, it is nothing but the value of lambda m extrapolated to 0 concentration. Okay. Now, so therefore, this is called the limiting molar conductance or molar conductance at infinite dilution. Molar conductance at infinite by infinite dilution. One can understand like this, that it is a state of dilution at which if you further dilute the solution, there is no perceptible change or there is no further change in the conductance value of the solution. So, that is called the state of infinite dilution. So, therefore, if you have a strong electrolyte, if you plot like this, then you have got certain points. So, these are all measurable things. So, you measure and then you extrapolate, just because the trend is linear. So, you extrapolate. So, wherever it is wherever it is cutting the y axis is nothing but lambda m 0. So, for strong electrolyte, the job is easier, that you can measure the value of lambda m at the infinite dilution condition. But the problem comes when you have this weak electrolyte, that like acetic acid, then you cannot apply this this extrapolation procedure to find out the infinitely dilution condition, this lambda value. Okay. Now, so in that case, what you can do? So, it was first proposed by Choleras long time back, that Choleras in long time back, it is called the Choleras law of independent migration of ions. So, what was the observation? Observation was like, if you measure like lambda m 0 for say KCl, and then lambda m 0 for NaCl, and then again if you measure lambda m 0 KBr, lambda m 0 NaBr. I mean, if you take a difference of lambda m 0 for KCl and NaCl, then KBr, NaBr, or lambda m 0 Ki 0 NaI, it is found that its value is say close to 23 Siemens centimeter square mole inverse, okay, at some given temperature. Okay. In the same way, lambda m 0 NaBr minus lambda m 0 NaCl is equal to lambda m 0 KBr minus lambda m 0 KCl, and that comes out to be close to 2 Siemens centimeter square mole inverse. That is your molar conductivity at infinite dilution. If you take the difference, it is found that this is following like this. So, this is a very strange behavior, that for electrolytic conductor, electrolytic when we talk about the electrolytic conductance, then it is very strange that KCl minus NaCl, KBr minus NaBr, Ki minus NaI. So, you see that here these co-ions, here also co-ions, you see if we want to take the difference of this lambda m0 with same co-ions, then this difference K plus Na plus, this is K plus Na plus, this is K plus Na plus, this difference is almost same. In the same way, this co-ion sodium same, this co-ion potassium same. So, Br minus Cl, Br minus Cl, they are following the same trend. So, this is a strange behavior. So, it is proposed that at infinite dilution something is happening. What is exactly happening conceptually? That I already have explained to you or discussed that the conductivity of a solution is dependent on the number of ions, charge carried by ions, and speed of ions. So, when you have reached the state of infinite dilution condition, then the number of ions present in unit cube, it is also fixed. Then charge on the ion, it is already fixed. Only thing is that the speed of ions. Now, speed of ions is an important factor for the transport of electricity from one position to the other. Now, if the speed of ions is not changing any further due to dilution, as I mentioned to you that state of infinite dilution is nothing but that can be stated in terms of conductance, that if you further dilute the solution, it does not bring in any change of the conductance of the solution. Therefore, no further change is happening even if you dilute. That means, when you dilute a solution, say a concentrated solution, then suppose initially say there are two ions like this. So, they are interacting one with another, and this is that will be a natural consequence, because this one is charged, this one is also charged. So, there will be charge interaction and many other factors, maybe solvation and other factors are also important. So, when you dilute means it is separated. So, interaction between this ion and that ion is expected to be reduced. Okay. So, therefore, if this ion is moving, if they are in close proximity, these two ions are in close proximity, then the movement of this ion is expected to be affected by the movement of this one and vice versa. But if you keep on diluting, then a situation will be reached when this ion and the other ion, they are so much separated that practically there is no effect of the interionic attraction or the influence of this ion on this one. So, therefore, the ions can move freely. So, when ions can move freely, that means they can freely contribute towards the conductance of the solution. Okay. So, that is why at infinitely dilute condition, this one is independent, this one is independent. So, their difference in conductance or molar conductance is also independent. I mean, it is not also dependent on the co-ion, because co-ions are also separated from one, I mean from this one, this ion or this ion, separated a lot. So, that is why the difference is nothing but the difference, I mean here KCl minus NaCl, KBr minus NaBr, they are following the same trend. So, that is called the Choleras law of independent migration of ion, and basically you can write at infinite dilution lambda m 0 KCl is nothing but lambda 0 m K plus lambda 0 m Cl minus. Okay. So, in the same way, if this electrolyte is having more than one ion, so accordingly you need to have some stoichiometric coefficient to be included over here. Okay. So, therefore, basically at infinite dilution condition, each ion will contribute, each ion will contribute to a definite extent toward the total conductance of the solution, And let me write some numbers, I mean some of these numbers for different ions, few ions I have, I will just write for you. So, lambda 0, it is Siemens centimeter square mole inverse. For H plus it is 349.6, for OH minus it is 199.1, K plus it is 73.5, Cl minus it is 76.3. So, you see that for different ions this contribution is different. Okay. So, therefore, see this independent ion migration, this concept has to be applied in finding out the conductance of the, I mean in finding out the lambda 0, this lambda m 0 for weak electrolytes. I mean direct finding out of this lambda m 0 for weak electrolyte is not possible, although that is possible for strong electrolyte. In that case, indirectly you have to find out the contribution of this, contribution of these ions, individual ions, and then you can find out this this lambda m 0. So, this much for today. So, we will take up this issue, I mean how to find out, I mean how to make use of this lambda m 0 for weak electrolyte in finding out some important characteristic quantity of the weak electrolyte. So, what we have learned today? So, we started with this conductance. Okay. Now, we have talked about this metallic conductor, then some idea of the basically this insulator, then this semiconductor. We have just given some example, that is it. And then we entered into this electrolytic conductor, because in electrochemistry this is relevant in electrochemistry. So, electrolytic conductor we have entered into, and the cause of this this conductance we discussed, and then we have used this the concept of simple chemistry concept to know how this this conductance and specific conductance, these will vary as a function of concentration. So, and we try to understand this this variation of molar conductance as a function of concentration for strong electrolyte, and for weak electrolyte the direct determination of this lambda m by this graphical extrapolation is not possible. So, in that case we need to find out this some roundabout way in getting the value of lambda m 0 for weak electrolytes, and we will take up this application of this lambda m 0 measurement for weak electrolyte in the next class. So, till then, that is all for today. Thank you.